has been given here. The transfer function gs is given by 1 by s square plus bs plus c, and that's the input for you, 1 by s, which is a unit step response input, and then your output will be given by this form, right? 1 by output will be given by 1 by s square by s open bracket s square plus bs plus c, and this you can actually solve using partial fractions expansion. And once we have partial fraction expansion, which is given by a by s plus b by s plus r1 c by s plus r2, from here you have the 4 possible cases that we have discussed about. That is when the r1 r2 are real and distinct, r1 r2 are real and repeated, r1 r2 are real are both imaginary, and finally r1 r2 are complex conjugates. Right, this is what we have looked at. So the first case is when the roots are real and distinct. So we take up the transfer function given by cs is equal to 1 by s square plus bs plus c, and then you equate it to you use partial fractions to expand it, and since the roots are real and distinct, we'll have 3 terms here. So 1 k1 plus k2 e to power gamma 1t plus k3 e to power gamma 2t. So this is actually a system, this is your system in place, and you have the exponential terms in between with the constant multiplied to it, and therefore this system will be actually an overdamped response. Okay, something like this. All right, so this is actually very similar to your first order system. There's not much difference about it, right? And the exponential terms here gives you this exponential growth, a little bit of exponential growth that is given here, right? So that is what the response is when you have real and distinct roots. Now when you have real and repeated roots, what you have is a by s plus b by s plus r1 plus c by s plus r2, and then yes, you equate them to the same thing. The only thing different between this first two is that this third term here gets multiplied with the time factor here, right? That is the difference between the three. And then this system is known as critically damped response. You'll have a very this type of response by which you can actually look at this the graph which is actually given here. It's very similar to that of the real and repeated root case, right? A real and distinct root case. It's not there much of a difference between the two, except for this term that is there in the third expression here, right? So that is the second case for you. Then the third case is when both the roots are imaginary. When both roots are imaginary, you will have cs equal to given by omega squared divided by s squared plus omega squared. This can be equated again using partial fractions, a by s plus bs plus c s squared plus omega squared. Since these roots are both imaginary, you equate it to this form, and then your inverse Laplace transform will give you k1 plus k2 cos omega t minus phi, which will give you an undamped response. That means you will get oscillations here, right? Oscillations here, and this is how you will have when both the roots are imaginary. And the fourth case is when the roots are complex. Now when the roots are complex, right, you again the same system comes in place, but here instead of just simply getting an undamped response like we did in this upper case here, the above case there, what we'll have here is that yt will be given by k1 plus k2, and then this exponential term will come into play here, right? And cos omega t minus phi. So that is the difference here. This actually the like just in the case that you have the upper case here, when we had this case k3 being multiplied by t. In a similar way, in this other case here, what we'll have is your third term here, your second term here will be multiplied with the exponential term, and that term will give it a response which looks something like this, right? Known as the underdamped response. This is the underdamped response that I've seen, right? This is the response that it's going to look like. And yes, of course, you have to remember that because of this exponential term, sometimes you have to remember the exponential term can be exponential growth or decay. So in this case, it's a decay. So this will restrict the basically this particular function is actually this second term, the cos term here, will try to make this the response oscillatory, right? But because of that exponential term out there, that will restrict it, and this will not be able to oscillate, right, freely, thereby decaying it and giving it the underdamped response. So basically, um, what is exactly S? What exactly the two roots here? The two roots are given by S12, which is sigma plus j omega and sigma minus j omega. Remember this, we got it from the Laplace transform, right? The S term there, which is actually given by sigma plus j omega. All right, so that is where you will get your roots from, and these roots are complex conjugates as shown by this expression. S12 is equal to sigma plus j omega and sigma minus j omega. So that is the response of a second order system. Now let's just take a general form of a second order system. Right, given Cs by Rs is equal to Kv divided by tau S square plus S plus Kv, then this can be reduced in this form, multiplying both or dividing both numerator and denominator by tau. You get this Kv by tau S square plus S by tau plus Kv by tau, and then this gives you the standard form of the second order equation. So if you look at it and you compare with this one, right, this second order equation given by Cs by s equal to omega n square, s square plus 2 zeta omega n s plus omega n square, that is actually a standard form for second order. All right, please have this expression, you look at this expression again. This is this general expression of second order. So this is the general expression, general expression of a second order system, all right. So once this in place, you can define a few parameters, which is here, zeta being the damping factor, which is 1 by 2 kV tau, and when there's no damping, omega n is known as the undamped natural frequency, so that will be given by kV by tau. All right, so this is your omega n, and your denominator here, which is s square plus 2 zeta omega n s plus omega n square, there will actually be called a characteristic polynomial, right? The characteristic polynomial, and this will actually be equated to 0 to get the roots, and then you can easily get the roots by solving this quadratic equation. So minus b plus minus root over b square minus 4ac, and then you do the needful by twice a, sorry, you do the needful calculation, you get minus 2 zeta omega n plus minus 2 omega n zeta square minus 1 by, because 4 and omega n gets out of the root, right? And then you get the roots to be minus zeta omega n plus minus omega n root over tau square minus 1. So that is how you can actually get out the roots of these characteristic equation. All right, it's very simple. Okay, once we do some problems, it will be very clear to you all. Right, now let's take a look by giving one example here. All right, so let's take another example. Basically, a given transfer function is given to you all. Let's the response and then rs is also given by 1 by s, so you can easily find out a few things here. When so when you take such a transfer function, if you put b is equal to 0, by that I meant that there's no damping, right? When there's no damping, so your s will be given by plus, the roots will be given by plus minus root plus minus j root over c. All right, because b is 0 here, so that is why your sigma will be disappearing, right? Because sigma is actually something to do with the second term there, so it's going to be missing from there. Only j term will come here, and then omega n will be equal to root over c, right? Because omega n is actually, omega square is actually supposed to be there. Now if you compare with that equation there up there, so if you compare with this equation, s square plus 2 sigma omega n s plus omega n square, this is s square plus 2 zeta omega n, right? S plus omega n square. If you compare with this one, this term is not there, right? B is equal to 0, so this b is equal to 0, so you will not get anything there. omega n square is actually compared to c, right, which will give you omega n equal to root over c, right? I hope it's clear. And of course, for an underdamped response, by which I meant when b is not equal to 0, then of course you'll have sigma plus minus j omega n s12, right? All the roots will be given by sigma plus minus j omega n, where sigma is equal to nothing but minus b by 2, and there your zeta will be equal to sigma by omega n, and which will give you b by 2 by omega n, which implies that b is equal to 2 sigma or 2 zeta omega n. So that is a few problems, a few expressions, field relationship in this underdamped system. All right. So with that, we'll just take a look at one example here, and we'll just solve a few things here. All right. So let me just take you to one example given by gs is equal to 36 divided by s square plus 4.2s plus 36. You have to compute the following, okay? Zeta, omega n, and the roots, and s12, right? S12. So for this, omega n is very simple, right? Omega n is actually, this is, if you compare with the main equation, so let me just write down. So let me put a constant here. So constant, let's put any constant. Let's put say just c, constant c. This is the general form, right? S square plus 2 zeta, right? 2 zeta. Just, can someone help me? 2 zeta omega n s plus omega n square. Thank you. So omega n is actually omega, this is actually omega n square. So this omega n is root over 36. It will give you 6, right? And this 2 zeta omega n is equal to 4.2, right? Because this, if you compare this b term there with this, you will get this. So omega n is equal to 6, right? So 2 zeta omega n is equal to 6 into 6 is equal to 4.2, right? And then you can take out what is zeta is equal to 4.2 divided by 12, right? And this will approximately give you some value there, right? So find out that value. So, and finally, your two roots s12 will be given by minus zeta omega n plus minus omega n root over zeta square minus 1. So can you quickly find out this value? Find out this value quickly. I will wait for you all to find out this value. So given this equation, you find out this value. All right, can you do it, please? Minus 7.365 and 3. So those are your roots s12. Okay. So two values, of course, because this is a quadratic equation. So that is what you will get from here. All right. Another thing that can be used using this particular relationship is omega d, which is actually your damped natural frequency. Omega d is actually your damped natural frequency. Okay, your damped natural frequency. Damped natural frequency. So here you just have to put down that omega d is nothing but omega n root over 1 minus zeta square. 1 minus zeta square. So this you can easily find out what is omega d also by using this simple formula here. So some problems will also be you can easily solve. Okay, so that is what we have for when it comes to a second order system. Now we'll quickly look at other things, which is your maybe your steady state error, and then your type of feedback control systems, and we'll actually look at those few things in the following days, and we can discuss it. And after everything has been done properly, we'll again look at a few examples, do a proper examples, and then come to such problems again. So if you have any questions, you can ask now.